Okay, so welcome back to this next video in which we are discussing the definition of a group in mathematics. Okay, right, so I'll remind you of where we've got up to so far. So what we have said is that we are trying to create new number systems. Okay, so what we start off by doing is creating a set of symbols which can be finite or infinite. Okay, and the set of symbols I've created is a finite set. I've got these three symbols here, capital Phi, lowercase phi, and capital D. And then what you need to do in order to actually turn that into a group, at the moment it's just a set. In order to turn that into a group, what you need to do is define a composition law on that set, basically. So you need to define what any element little x composed with any other element little y within this set is going to be equal to. Okay, so you need to define one of these composition tables, and it isn't necessarily true that little x composed with little y is equal to little y composed with little x. It doesn't necessarily have to be symmetric down that line in order to be a group. We're going to see that that is not one of the axioms of group theory. Okay, right. So we're currently going through the properties that this composition table does have to obey in order for it to be considered a group. Okay, so the first one I've said, which is a nice easy one to understand, is closure, and that means that all of the answers, all of these 9 entries, need to be elements within the group. So whenever you compose one element with another element in the group, you have to get a third element within the group. You can't suddenly get a new symbol that we haven't got in our original set, basically. Okay, so that's closure. The one that we are trying to understand at the moment, which is a very much so non-trivial property, this is a biggie, okay, associativity. Okay, and what this is all about is composing 3 things together. Okay, now there are 2 ways that you can compose 3 things together. Either you can put the brackets around x composed with y here, okay, and that means compose x with y first, get the answer, and then compose that answer with z, okay, or you can put the brackets in this other position. You can say firstly compose y and z together, and then take x and compose it with the answer of y composed with z, okay, and basically associativity says that those 2 ways of composing the 3 things together have to give you the same answer, and that is completely non-trivial, basically. You might think that that's trivial because all of the number systems that are studied in classical algebra automatically have that true, okay, and you just think of that as something that has to be true. But if you're just defining a composition table abstractly in this way, you probably will not achieve this, basically. This will not be true, basically, okay, unless you know what you're doing or you get very, very lucky. Okay, right, so what I now want to do is talk about a way of actually building a group so that it obeys this, because there is a way of doing it. Okay, if you just set about trying to put in answers in these sockets here, in these plugs, okay, if you just set about trying to make up a composition table on your own, you will really, really struggle to get it to obey this, even when you've only got 9 things to fill in. It is a real puzzle. Okay, however, there is a simple way of building a group so that it does obey this, building a composition law that does obey this, basically, and I want to tell you that now. Okay, right, so the way of building a composition law so that it obeys the associative property here is to let these symbols within your group, okay, let these symbols here represent permutations of some set, and let the composition of the symbols in your set represent the composition of these set permutations. Okay, so I've just said something that might mean absolutely nothing to you, so let me now explain what I mean. Okay, so I'm going to take a very, very simple set to take set permutations of. Okay, you could take much more extravagant sets than this. I'm going to take a set that contains 2 symbols. Okay, the symbols A and B, like so. So I've got a little set here, which is a set containing 2 things, A and B. Okay, now, what I need to tell you about is what is a set permutation. Okay, a set permutation is a bijective map from this set to itself, basically. It's a map from the set to itself. So really all it does is rearrange the elements of the set, basically. It maps elements of the set onto other elements of the set. So let me show you the only two set permutations that actually exist for this incredibly simple set. Okay, and because it's such a simple set, only containing two elements, there are only two set permutations. With bigger sets, there will be far more set permutations. So let me show you the two set permutations. So I'll draw them out. So here is our set here, and basically I'm going to map the domain here, which is our set, onto our range here, which is the set again. Okay, and the first simple set permutation is just mapping A onto A and B onto B. Okay, so that's a set permutation. It's a bijective map from the set here onto the set itself. Okay, and then you might be able to guess what the only other set permutation for this very simple set is, which is the map which maps A onto B, okay, and then B onto A. Those are the only two possibilities, basically. Okay, right, so it looks as though I've gone completely off topic. Okay, that's wonderful. That's what a set permutation is. That's the two set permutations of this set AB. What does this have to do with producing composition laws which are associative? Well, here's how I can produce a composition law that is associative. What I can do is I can give these set permutations symbols. I can give them names, if you like. I can represent this set permutation here as the identity map, okay? So I'll give it the symbol I, okay? Because it maps everything onto itself, we can call it the identity map, okay? What should I call this one? Well, it's often called a transposition, so people often use tau to represent that for transposition because it's transposing the two elements here. So what I have now done is I am saying we are going to call this set permutation of my set up here, which is the identity map. We'll call that I, okay, we'll let that be represented by the symbol I, and I'm going to call this transposition map here, I'm going to let that be represented by the symbol tau. Okay, now here's how I can build a group, okay, or rather a set which will have a composition law which is associative, because I haven't told you all the axioms of group theory yet. It actually will end up being a group, but we'll have to do a bit more to understand why. Okay, right, so what I'm going to do is I'm going to build a set, okay, which contains these two symbols, I and tau, so it contains these two symbols which are now both representing set permutations. So this is how I'm going to build a group, by putting these symbols that are representing set permutations of my set here into a set themselves, and I'm going to define a composition law on this set. Okay, so now I'm going to define a composition law. So now I've gone even more simple. I'm just building a number system out of two symbols. Okay, so let's do the composition law now. Okay, now how am I going to define this composition law? Well, quite simply, I'm going to define composition of two symbols here to be what set permutation do you get when you compose the two set permutations together. Okay, so for instance, when I say little x composed with little y, what I'm going to say that's going to be equal to is it's going to be the set permutation that you overall get if you do y first. Now pay attention to this. We're going to do y first and then x. Okay, that's standard, that this one here is the permutation that you do first, and then this one will be the permutation that you do afterwards. Okay, right, so let's now work out the entries in this composition table to make this a little bit more obvious. So we'll start off with the entry here. So we want the identity composed with the identity. Now I'm saying that to work this out, all I have to do is compose the mappings with one another. Okay? So what this means is do this mapping first, so that's just the identity, so that'll map A onto A and B onto B, and then do this mapping again. So now I'm going to map A onto A and B onto B again. Now what is that overall map? Well, I'm mapping A onto A and B onto B, so it's still the identity. So I composed with I is going to give I, basically. Okay, so this is how I'm going to define composition, just as the composition of maps. So let's continue on. Let's do I composed with the transposition tau. So this means do the transposition tau first. Okay, so that means map A onto B and B onto A, and then do the identity afterwards. Okay, so that now means send A to A and B to B. What is this composition overall? Well, we take A to B and we take b to a, so that overall then is tau basically. So the answer to this is tau. Okay, next up let's do tau composed with the identity, and we're rapidly running out of space here, but never mind. Okay, so this means do the identity first, so we'll map A onto A and B onto B, and then do the transposition, okay, where we'll map A onto B and B onto A. Okay, now what overall is that now? Well, we're going to map A onto B and B onto A, so overall again, that is just the transposition. Okay, so those two composed together will equal tau, and then finally, tau composed with tau, if we want to work out what that will be, we're just going to do the transposition twice this time. So we'll do it once here, okay, and then we'll do it again. Okay, and what overall is that map now? Well, A is going to be mapped onto A, and B is going to be mapped onto B, so that goes back to being the identity overall. Okay, so what I have now done is built a composition law on this set of symbols by remembering that I'm letting these symbols represent these set permutations, and then to work out how I compose two elements here together, all I'm doing is composing the two set permutations that they represent together to get another overall set permutation, and then whatever that overall set permutation is, I'm putting that as the answer basically. Okay. So, this is the way that you can build composition laws that are associative. You can let your symbols in your set which you want to make a group, you can let those represent permutations of some other set, as we did here. Now, why is this always going to obey associativity? That's the big question now. Why does it always obey associativity? Well, maybe if I give you an example, it will become apparent as to why that is. Okay, so remember, associativity is all about composing three elements together. So let's just take an example. Let's take the identity composed with tau, composed with tau. Okay, now from my composition table, if I want to do this, what I need to do is either I need to compose I and tau together first, and then take that answer and then compose it with tau like so, or I need to compose tau, well actually I shouldn't put equals because we don't know that associativity holds yet, okay, or I need to put I composed with tau, okay, so basically if we were doing a composition table that didn't obey associativity, you would have to tell me exactly which one of these you meant, because it wouldn't, you know, if our composition law didn't obey associativity, then these wouldn't necessarily be equal to one another. So you couldn't just write this and assume that that has one answer. Okay, you'd have to put one of these specifically. I'm going to say we want our groups to obey associativity. We want the composition law to obey associativity. And indeed, if you build your group in this way that I've described, by letting the elements represent permutations of sets, then it will obey associativity. And I want to show you why these two things are always going to be equal, and hopefully you will see then that that will generalize to any elements A, B and C that you put in here, or X, Y, Z that you put in there. Okay, right, so let's do this. Okay, well, basically the reason that associativity holds here is that this actually has an answer when we think about composing set permutations together, because if we think about our elements of the group as representing set permutations and the composition of the elements of the group as representing the composition of the set permutations, then composing three set permutations together has a meaning, okay, outside of the fact that the group composition table can only compose two together. Obviously, if we're talking about set permutations, you can compose three together. So let's just write this out, and then let's interpret what this and this mean, and we'll see how associativity ends up being true. So what this means is do tau, okay, the first mapping that we're going to be doing is tau, so we'll swap A and B around here, okay, like so. Then do tau again. Okay, so we'll swap A and B around again. Okay, and then finally do the identity. Now this is what I mean when I say that it has an answer. Composing three things together like this, where you're thinking of these as representing set permutations, and the composition as just representing composition of set permutations, that has an answer. It has only one answer. So we better hope that these two things must give that answer, and that therefore they must be equal to one another. Okay, so what do these two things mean? Well, if we start with this one first, actually, what this would mean is firstly combine tau and tau together, okay? And then take that answer and compose it with I. So what this would really do is it would say, okay, work out what these two composed together are first, and then combine that with this one here. Okay, so if we work out what those two combined together are first, they're obviously the identity when they're composed together. Okay, so this portion in blue brackets, this reduces to this. Okay, and then we'd be composing the answer to this here. So this portion in blue here is the answer to that. We'd then be composing that with the identity here. Okay, and then we'd get the answer to that, which of course is the identity. If we did it this way round, what we'd say is firstly compose together I and tau. So it would say do these two bits together, get an answer, and then compose that portion with this portion here. Okay, so it would say leave that tau out the front here. Okay, so we'll have A being swapped to B and B being swapped to A out here. And then we'd be combining these two bits together. And of course, when we combine tau and I together, that just gives us tau. Okay, so I've reduced now the purple bit down to here by composing those two together first. And then I'd compose these two together. Okay, so of course, these two do overall give the same answer. And I hope that's illustrated to you why, when we define composition in this way, when we think of the elements of the group, this set that we've defined the composition law on, as representing permutations of some set, and we think of composition of the elements as representing the composition of the set permutations that those elements represent, then associativity has to be true, because when you compose three elements together, it really doesn't matter how you put the brackets, basically, where you put the brackets. This has an answer. Three things composed together has an answer. It shouldn't matter whether you first work out what these two combined together in purple are, and then compose that with this bit outside, or whether you first work out these portions in blue here, and then combine that with this portion outside. That doesn't matter, because this has only one answer. Okay, you can follow this through, and it maps A to A and B to B. Okay, so that's really where associativity comes from. It comes from thinking about the elements of a group, or the elements of this set that we've defined composition law on, representing set permutations, basically, of some set. Okay, and the composition law as representing composition of those set permutations. So that is how you can build a composition law that obeys associativity, by letting your symbols in your set represent permutations of some set, and then letting the composition just be the composition of these set permutations, basically. That's how you can build an associative composition law. Okay, and really that's the only way I know of doing it. If you just sit down and try and fill in these answers how you want, you will really, really struggle to achieve this, basically. It is really, really difficult if you're just building these however you want, okay? But if you are thinking of the composition as representing this composition of set permutations, then it becomes a lot easier. Okay, right, so that's really the core of associativity. It's all about the composition of set permutations, basically. Okay, right, so we'll call it there for this video, and in the next video what I'll do is I want to show you firstly how you can think of the integers under addition, which is this example of a group that we're hoping to eventually show as a group once we've finished all the definitions. I want to show you how you can think of that as being a set of symbols that are representing set permutations, okay, because you might never have seen that before, and I'm telling you that you should really think of the elements of groups as representing permutations of some set. Okay, so I want to show you how you can think of the integers as representing permutations of some set. Okay, then what we'll do is we'll extend associativity out, because I've done it for composing three elements together. Okay, we'll discuss how it extends. Once you've got that this is true, it automatically implies that composition of an arbitrary string of elements, it doesn't matter where you put the brackets, basically. Okay, it has one answer. Okay, and that should follow very nicely from, again, thinking in terms of the elements as representing set permutations and composition as representing the composition of those set permutations. Okay, and then we'll go on to the two other axioms that groups must obey.